Hello, back at EK307 lab headquarters. So right now we're going to be measuring the dynamics of an RC circuit, like how it responds to a transient change. So we have our circuit right here. We have an R, it's 5.1 kiloohms, connected to a capacitor that's 0.1 microfarads. That's being driven by a function generator that's generating a square wave at 10 hertz. Then on our oscilloscope, we're looking at the outputs and the input. So the input to the circuit is in yellow. Looks like a step response, and the output is in green, and you can see the charging of the capacitor as the voltage asymptotes to the step size. So the objective here is to learn how to figure out the time constant by looking at the screen on the oscilloscope. So before we do that, we'll look at the math really quick. So here we have our circuit that we are going to be analyzing. We have a unit step, so you could imagine that at time t equals 0, the step goes from 0 to 1. We're approximating that with a low frequency square wave. So the voltage across the capacitor is going to be a function of time, and it's going to equal its initial conditions plus the change in the voltage of the step times 1 minus e to the minus t over tau. And we know that tau is the time constant, and for an RC circuit it just equals RC. So that's this tau right here. Close that parentheses. So there are a few things that we could cross off this equation really quickly. So first one is the V0 is the initial voltage condition, and it's 0 right there. So we could just take it out of the equation. And delta V is going to be 1. I call delta V the displacement voltage, or how much the step changes from its initial condition to the step after the transition. In this case, we have a unit step. It goes from 0 to 1. So the change in the voltage is just going to be 1. So now we have 1 right here. And then if we distribute this, just distributing the 1, the math is going to be pretty easy. So it's going to be 1 minus e to the minus t over tau equals Vc of t. So we could analyze this for a few different conditions. So first condition, we're going to say when t equals 0. And so if we have t equal to 0, then this is going to be e to the minus 0, or 0. We know that an exponential to the 0 is going to be 1, so 1 minus 1 equals 0. And that makes sense, and it lines up with our oscilloscope right here. Just as you could say at t equals 0, it could be 0 minus or 0 plus. The voltage on the capacitor is 0 because it can't change instantaneously. That all looks good. So there's another interesting condition, and that's when time equals tau. So when time equals tau, I'm just going to rewrite the equation, 1 minus e to the minus tau over tau. And then we know that tau over tau is going to be 1. And e to the minus 1 is 0.37. So that's saying that if we have 1 minus 0.37, that equals 0.63. So what this is saying is that when we've gone one time constant worth of time, in other words, when the time equals the product of r and c, we're going to have this condition where e to the minus time over tau is going to equal, well, the time over tau is going to equal 1, so then e is going to be e to the minus 1 equals 0.37, so it's at 0.63% of the way to the final value. So I could just graph that really quickly right here. So if we consider that this is 1 volt, unit step response, this is the voltage across the capacitor, 1 time, which is on the horizontal axis right there, equals tau, we're going to have displaced, or gone 63% of the way to our final value. So that would be 0.63 volts. Right here. Now, how does that, how can we use that? So, well, if we can look at the oscilloscope here really quickly, if we could figure out, by measuring on the oscilloscope when we've gone 63% of our displacement voltage, or 0.63, then we could measure the time it took to get there. And with these modern oscilloscopes, there's a nice way to do that, so we don't need to use rulers anymore, we could use something called the cursors. So I'm going to make my time base a little bit smaller so I could see some more of the waveform. So on this oscilloscope, if I push the cursor button, it brings up these cursors, which are little lines that I could move back and forth. And when I do that, they mark off time and voltage. So the first one I want to do is set my voltage cursor. I'm going to set the baseline cursor down here. And then if we look at the values here, it might be a little small, but it's really confirming that we're at 0 volts, plus or minus a few millivolts. Now I set my second voltage cursor, Y2. I'm going to bring it to the top of my step voltage. And what I'm doing now is I'm just verifying that indeed the voltage of the step is what I think it is. And it's supposed to be 1 volt. It's very close to that. It's like 0.987 volts. So we could assume that's 1 volt for easy math. And because we don't have a ton of precision here, that's okay. So we know that the step size is 1 volt. So then I could take my Y2 cursor and bring it back down to 0.63% of that, which is going to be 0.63 volts or 630 millivolts. So I'm bringing that back down. So 630 millivolts is right here. Oh no, touch the screen. It's one of the bad things about a touch screen. So you can see, we're crossing that line there. So now I could change to my time cursors. So first I'm going to mark where the step started with cursor 1. And then I'll use cursor 2 to mark when my voltage cursor, which is at 0.63, intercepts with my waveform, with my capacitor charging voltage. So now I look at the change in time, and it says 520 microseconds. So if we go back to our board right here, so we had a C of 0.1 microfarads and an R of 5.1 kiloohms. And if I do the math right there, I get 510 microseconds for my time constant. And so that lines up very close with what we're getting here. So our delta is actually saying 520 microseconds on the scope. But considering I've been eyeballing this and the lines are fairly good, that's not a bad approximation.